Let's just say we start with some weak dipole field. That field passes through the liquid outer core, which is an electrical conductor. Conductors have this cool property that they drag magnetic fields with them. So, if the entire core is rotating with the Earth, then the magnetic field will also rotate. But remember that the rotation of the outer core gets faster towards the center. As a result, the starting magnetic field gets wound up into rings around the axis of rotation, into a torus shape. Now, cut to the second type of motion in the outer core. You have these streams of conducting material twisted into helices by the Coriolis force. Those flows grab hold of our toroidal magnetic field and twist them up further into many little loops. Those loops form magnetic tubes around the Earth's rotational axis. These in turn generate toroidal electric currents. If quantum fields are a buzz with particles popping into and out of existence, then the so-called zero-point energy of those fields should not be zero. Completely empty space should have some real energy. It should have vacuum energy. In 1948, the Dutch physicist Hendrik Casimir came up with a brilliant scheme to detect this. He imagined two conducting plates brought so close together that only certain virtual photons could exist between the plates. In the same way that an organ pipe or a guitar string of a particular length only resonates with waves of certain frequencies. Any non-resonant virtual photon would be excluded, reducing the vacuum energy between the plates. However, on the outer surface of the plates, all frequencies of virtual photon are allowed. The higher vacuum energy outside compared to the inside of the plates should result in a pressure differential that pushes the plates together. The Casimir effect was only successfully measured in 1996 by Stephen Lamoureux at the University of Washington, based on the initial ideas of his student Dev Sen. When separated by less than a micrometer, conducting surfaces were found to be drawn together by a force that matched the predictions of quantum field theory. Now, while there are potentially other explanations for the observed force, this has been taken as strong evidence that vacuum energy is real.
I think it might have actually been during a talk by Juan Malmacena about dr equals EPR that I started to wonder to myself, could traversable wormholes exist, right? And people thought it was fascinating as an exotic configuration of space-time, but I think many people probably suspected that it couldn't work. So we saw that it could.
One of the magical things about quantum mechanics is you can actually have negative energy, and this allows you to do things that you would have thought otherwise were impossible.
What Daniel Jaffers showed was that if you introduce what's known as a negative energy shockwave, you can support your wormhole and get something from one end and have it come out the other.
Yeah, today I'm going to talk about human traversable wormholes. My talk will be based on two papers. The original construction from 2 years ago, which first proposed using Casimir energy to build traversable wormholes. And then the second part of my talk will be based on this recent paper for how to embed those in the interrandall syndrome model and make them humanly traversable. So what are the traversable wormholes? So this is a picture just of a wormhole. So we have two space regions which are connected by a handle. And we say that its wormhole is traversable if an observer can actually travel through the handle. And it is humanly traversable if a Homo sapiens can travel safely. And I would like to point out that safely means it's safe for both the Homo sapiens and the wormhole. Wormholes are actually quite fragile too, but in a different way. I will explain it in a bit. So in my talk, I would like to answer two questions. So do such objects exist in classical Einstein gravity in 4 dimensions without exotic matter? And again, in just in one slide, I will explain what I mean by exotic matter. And the answer is yes. And the second question is, can they be made humanly traversable with matter which is roughly consistent with the current observations? And the answer is yes. Although in my case, we did not include very stringent constraints, but at least the matter contact we're gonna talk about it makes sense. Okay, let me explain what I mean by not exotic matter. So these are the familiar Einstein equations where G Newton is just a constant, which is in our universe as this. And T mu is the stress energy tensor of matter. So the properties of the matter determine the properties of the space-time. And the traversable wormholes requires the so-called negative energy. And the physical reason for this is that there are two spheres inside the wormhole. It first shrinks and then expands. And so various theorems in Einstein gravity prohibit this unless we have negative energy. And precisely, let me explain what I mean by this. So if we have a simply negative cosmological constant, in some sense it does lead to negative energy, but this is not what we actually want. What we want is the violation of the so-called average null energy condition. So it means that we take non-extendable null geodesic, integrate the corresponding null component of the stress energy tensor along this null geodesic. And so this is a neck, and for a traversable wormhole, this quantity here, it should be negative. And a neck is violated by the famous Casimir effect. So I should point out that all classical matter satisfies this requirement. So, but the Casimir effect, it's quantum, so it actually violates this. So let me remind you what Casimir effect is by an example. Suppose we have a massless fermion on a circle of length L, so just in 2 dimensions, and we can impose antiperiodic boundary conditions and compute the difference between the energy on the circle and energy in flat space-time. So this energy difference is actually UV finite, and it equals to this. It's negative, and it leads to the following non-null component of the stress energy tensor. So this is precisely what we want. And notice that this quantity is proportional to the Planck constant, so it's small, so it's a quantum effect. But I believe that it has been actually verified experimentally. So one maybe technical comment is that in our case, the space-time will be curved, but the Casimir effect can be generalized to this case as well. We just need to take into account the conformal anomaly. So this is again the picture of a wormhole, and indeed in this case, when we have a wormhole, we have one cycle which is not contractible, and this is very similar to the case with these fermions living on a cylinder, because they can go around this cycle. So when we introduce it, if we have matter, then it will produce a Casimir effect and produce negative energy. So this is the idea, to use this negative Casimir energy to construct the wormholes. But there is a problem, because we need a lot of matter, because not only we have to compensate for the Newton constant, but also we have to compensate for the Planck constant as well. And so one observation is this: we can actually use magnetically charged black holes for this purpose. So this was proposed in our paper with Juan and Fedor. Essentially, if we take magnetically charged black holes with charge Q, then it has been known for some time that free Dirac fermions in this background, they support two-dimensional fermionic modes. This is known as Kalin-Rubakov effect. It has been known since 80s, and it's valid not only for black holes, for monopoles as well. Perhaps I should clarify why are they two-dimensional. Let me just draw a picture. So this is, say, a two-sphere, and we have a magnetic flux coming in all directions. And roughly we have one fermionic mode per unit flux. So it means that this fermionic wave function is in fact localized on a scale of radius divided by the square root of Q. So if we go to the energy scales, to scales above this length, let's call this LB. Then we can essentially neglect the inner structure of this fermionic wave function, and we can just concentrate on its movement in the radial direction. So essentially they become effectively two-dimensional. So are there any questions on this point? So, okay, actually this equation, we should remember this because it will appear later in our discussion when I will discuss holographic matter. That the point is that below a certain energy scale, we can treat these modes as effectively two-dimensional, and they will have two black holes, then they can propagate along the magnetic lines. This is actually even observed in the on Earth, because you know that there are polar lights, because the charged particles from the outer space travel along the magnetic lines of the Earth. So you can see them in the poles. And this is exactly the thing which can happen between two magnetically charged black holes. These massless modes will propagate along the magnetic lines. And this is why it's good for us, because it means that all these excitations, they won't just spread around in 4 dimensions, but will travel exactly along this effective 2-dimensional cylinder. But there is a problem with this, because if we assume that even if we have some dark sector with this dark U1 gauge field, it requires an enormous number of fermionic fields in order to make it macroscopic and humanly traversable. So number of fermionic flavors should be 10 to the 52. So it's extremely unlikely that there will be a dark sector with this number of weakly interacting fermions. It means that one will have to tweak the coupling constant to be smaller than this number, because these fermions, they can travel in loops, and so the effective coupling constant is in fact multiplied by this, and it would be true even for gravity interactions. So such big number of fields would mean that they would strongly interact with gravity well below the TeV scale. So this is just does not make any sense. So then I guess one natural idea is that what we try to describe the matter holographically as well. So we say that we have a 2-dimensional CFT described by 5-dimensional random syndrome. And the question is, what happens in this case? Do we still have these massless modes or not?